Hello everyone. Today we are going to talk about AVO and seismic inversion for reservoir characterization. So, the seismic inversion. What is the seismic inversion? You can see in that slide you have two sections. The first section, let me activate the pointer. So the first section, the upper section, is the reflectivity section. This is a seismic reflectivity section, while the down section is the acoustic impedance section. So what is the difference between these two? The first section, the higher section, is the reflectivity, which is expressed you can see peaks and troughs. So these peaks and troughs is reflecting the interfaces between two different layers. So when you have two different layers, you have the differences between density and velocity for each layer. So at the interface between these two layers, you will have the reflection of the waves. So you will have peak or trough. So you can see from the seismic the interfaces between the layers. While for the seismic inversion, you can see the acoustic impedance for each layer. So the acoustic impedance is showing the layer itself, the properties of the layer itself. So this is the first thing and the first difference between the seismic and the seismic section and the inverted section. So what is that inversion? How we got the inversion? We start with the seismic section as an input in order to have the result of the inversion by removing the wavelet effect from the seismic. So this is what we call seismic inversion. You just remove the wavelet effect from the seismic data, and then the result will be the acoustic impedance or the elastic impedance. So you are going in the seismic inversion to use this technique in order to create a model for the subsurface. This model gives you a data about the subsurface because the acoustic impedance is equal the density and velocity. So the density and velocity is a function of the rock. When you have a certain rock, you will have a different velocity and different density for that rock. So it can express the rock itself and even also the parameters for the reservoir. So we are using the seismic as an input, and also we use the well data also as an input to do the seismic inversion. So the differences between the seismic and the inverted results is that the seismic having a low resolution and while the seismic inversion results having a high resolution because we removed the wavelet effect. So you can see here from that arrow, the black arrow here, it's showing the peak here, which is reflecting the interface itself. So what is the benefits of the seismic inversion? Why we are creating seismic inversion, or why we do that technique? Actually, the first thing come to your mind when you do the seismic inversion, you are going to enhance the resolution because you know the seismic data have a certain resolution, and this certain resolution can be controlled by the frequency that you have been used during the acquisition, in addition to some of the parameters that you have applied to the data on the processing. So you have a certain resolution for the seismic data, and when you are going to increase that resolution, you are removing the wavelet effect. So the wavelet effect, when you remove, it will give you the seismic inversion. Of course, we are going to talk on the next slides about the inversion itself and the mechanism of the inversion. But here we are going to just to show that the benefits of the seismic inversion. So the first benefit, you are going to have a higher resolution, higher than the seismic data. So the seismic data is characterized by the lateral extension, while the well-log data having a high vertical resolution, but on the lateral resolution it's very poor because you have scattered points for the well data all over your area. So we are going to use the power of the well data, the vertical resolution, the vertical resolution, which is very high vertical resolution from the well log data, and we combine with the seismic data, which has the lateral the lateral representation for the subsurface. So we having this combination in order to produce the seismic inversion, which has the high resolution for the acoustic impedance. So the first thing is to have a high resolution data. The second one, you can see this black arrow. This black arrow is showing or referring to the peak or the trough here for the in the seismic data. While you can see from the seismic inversion data, you have some certain differences from the same reflector. Focus again for that reflector here, the red reflector. You can see you have a high amplitude here. So this high amplitude giving you a feeling that you have the contrast, higher contrast between the upper and lower layers. But you can see that you cannot differentiate between any differences along the wavelength, along the reflector here. While from the seismic inversion data, you can see that you have some differences for the amplitude. The acoustic impedance here having some differences comparing to the surrounding acoustic impedance for upper and lower here. So we are still in the same reflector here, the same reflector here. We are having acoustic impedance for the same area here, for the same reflector, but you can notice that you have differences in the acoustic impedance. So this can reflect some of the petrophysical properties of the rock, as the inversion results is acoustic impedance, which is equal to the multiplication of the density and velocity. So the density and velocity will change according to due to the differences on the density and velocity, which of course can change or can differ as a result of the fluid content, the rock lithology changes, and all of this. So the petrophysical properties of the rock can be obtained also from the seismic inversion. So the second is the petrophysical properties that you can get from the inversion. The third is the lateral heterogeneity. From this example, you can see that you have a lateral heterogeneity here for that reservoir. So also you can identify that lateral heterogeneity from the inversion. And suppose you have this is a post-stack inversion, so we have acoustic impedance. But suppose you have the data, the seismic data, which is gathers the pre-stack seismic data in general, and then you have the ability to create the pre-stack seismic inversion. So the output will be the density, VB, and VS. So you can use this VB, VS, and density in order to predict the lithology, and sometimes you can predict also the fluids. So the benefits also can give you as an output a lithology volume, and also can give you a fluid volume. So the seismic inversion is you can notice that it can give you the representation, or can give you the geological model for the subsurface, and which represent what is beneath the earth. So you will have some benefits starting from the high resolution, and then having the petrophysical properties of the rock, and also identifying the lateral heterogeneity, and also generating lithology and the fluid volume. So this is the benefits of the seismic inversion. So we have in that inversion. So in order to know how the general idea of the inversion, We can start with this example. You have, in general, we have the earth layers here, and then we are doing the seismic acquisition. So when you do the seismic acquisition on the field, you are generating waves and sending these waves. So these waves penetrating the layers, and then some of that waves reflected on the interface. You can record this in your geophone or hydrophone, and the others of the wavelet penetrated and refracted and then go down for the other layers. So the wavelet, when the wavelet goes down, it convolve with the layers and then give you the seismic data. So this is how the seismic data is generated, and actually we call this modeling is a forward modeling. So this is a forward modeling to generate the seismic data. In contrast, if you have a seismic data and then we removed the wavelet from that seismic data, you are going back to have the acoustic impedance. And the acoustic impedance is a density multiplied by the velocity of the waves on that layers. So you will have the acoustic impedance, which can give you an insight about the rock, the rock that form the subsurface. So we call this as this modeling, we call it as a backward modeling, because you are starting from the seismic data and then you go back to the layers itself. We are trying to get more information about that layers in order to predict the lithology and the flows. So this is called backward modeling. For the seismic inversion methods, we have different classifications for the seismic inversion. This is depend on the type of the data that we have using and also the mathematical approach that we are applying. For the data that we have using, there is a post-stack seismic data and the pre-stack seismic data. If we have a post-stack seismic data as an input for the seismic inversion, so we call it post-stack inversion. We use post-stack inversion. But if we have the pre-stack seismic data available in addition to the S-wave, the sonic shear waves, so we can do the pre-stack seismic inversion. So according to the data availability, we can do post-stack seismic inversion or pre-stack seismic inversion. Of course, the results and the outputs of the post-stack differ than the pre-stack. For the pre-stack, you get more data and you can have the ability to differentiate between lithology and the fluids more than the post-stack. And of course, this can be confirmed before you do the inversion by using the visibility study from the well-log data. If we are looking from the mathematical approach that we apply for the inversion, so we have two different types: the deterministic and stochastic. Deterministic inversion and stochastic inversion. And the difference between the deterministic and stochastic, the deterministic is giving you only one solution, while the stochastic inversion giving you multi-realizations. So you can do the B10, B50, and B90 for the acoustic impedance and the elastic impedance for all of the outputs of the seismic inversion. For that reason, you can determine some of the uncertainty from the stochastic inversion, while for the deterministic you will have only one solution for the inversion results. The angle stacks data. When we are loading the data, we'll use the near and mid and far. So when we are using near, this near data is expressing the same point, near, mid, far. It's expressing for the same point. It's a reflection for the same point, but from different offsets. Okay, we are imaging the same point here, the same subsurface point. It's all of these are imaging the same point, the subsurface point. Okay, but sometimes we are measuring this point or reflecting this point or imaging this point from near offset. Of course, the amplitude from this one will be different than the amplitude we got from this one.
from the near offset, if we are shooting from this source and recording from this receiver, of course, you will measure this point. Try to imagine we have got this this reflector, okay, from the receiver number one, okay, and then we'll have the receiver, the shoot point number two, and the receiver number two. It will image also the same point, but of course, the amplitude will be different than the first one. Why? Because we have the distance may be greater, so the amplitude will be less. Then from the third one, you will have that maybe the amplitude is becomes smaller, okay? So you will have the same retraces for the same point, but the first one is measured from near, then the second one measured from mid, and then the third one measured from far offset. So you will have differences in this amplitude. And this is maybe expressed if you have a fluids, you can try to find these differences. Is it like this is what we call the AVO response? The AVO response, maybe this is due to the differences in the offset only, and if we have a the lithology, the same lithology, of course, but will give you the different response, or we have fluids that may be the cause for this one. Okay, so maybe you find that from near you will have this, and from far maybe you do not have this, maybe you have an reverse polarity. So is it what we called maybe the AVO classes that we are going to talk about it? Okay, but keep in your mind that the near and mid and far offset for the same point, but we have different measurement for the same point from different offsets. Okay, so if you have here the uh, the incident the incident ray here, this is the incident one, okay, and this is the geophone that we are recording the signals. So this is maybe high offset or far offset, and this one here is near offset, okay, or maybe close to zero offset. Zero offset means that the same source and receiver at the same point. Of course, it's not like this is a theoretical, not a practical, because you cannot have the source and receiver at the same point. Okay, but try to imagine like a zero offset. Okay, almost zero. Okay, and then this is far offset. So for this incident wave, you can analyze this ray to two components, which is horizontal and one which is vertical. Okay, and for this one, for the zero, you will find that you have also horizontal and vertical. But for the near offset, the horizontal is very, very small, so we can ignore this one. But for the far offset or mid offset, you will have the horizontal component will be considered. Okay. And of course, maybe like the vertical or maybe greater than this one. And so this is what we call the cause the shear. And when you cause the shear, of course, you will have the component of S wave. So if you have the component of S wave and B wave, of course, the vertical here, the green will be the compressibility, which is B wave. And the blue here will be for the shear wave, the shear stress, and maybe caused by the shear wave propagation. So you have now a P wave and S wave. Your source yield P wave only, but according to the angle, you have a generation for B and S. As you have the particle are moved horizontal and vertical, so if this ray caused for the particle to be um, moving or oscillating vertically and horizontally, so you have P wave and S wave. So this P wave and S wave, of course, will be the main reason for having the amplitude that you are recording here. So this recording here will be affected by the S wave. Although you do not have the multi-component geophone, you have the geophone that measure B wave only, but your measurement will be affected by the S wave because the S wave here will have a considered component. So this is maybe affect the reading of the B wave that you have. Okay, and this is the origin of the AVO. Okay, this is the reason for having the EVO. So you will have, if you have this shear and compressibility, of course, you will have a change in the rock, the B wave changing the density, changing the volume and changing the shape, while the S wave changing the shape. So you will have here a new term which is called Poisson ratio. So the Poisson ratio is expressing a relation between the vertical and the horizontal strain. Okay, you have the original in gray. This is the original cube or the original volume that we applied the B and S wave on it. So the result one will be this violet color. So the change, the relation between the vertical and the horizontal strain expressed by Poisson ratio. So you will find that this result shape, according to the original one, this is measuring or giving you the indication for the Poisson ratio. Okay. And this is, as we said, this is occurs because we have the incident B wave here, but the reflected will be shear and will be BO. So in this slide, we are going to use the these gathers here. So we have for the first one, which is class 1, we have in class 1 here. This is the near trace, and this may be this here, the mid, and then we have the far here. Okay, so try to find. We have here high amplitude. This is high peak. Okay, and try to find this. Try to notice you have high peak here, and then this peak is becomes lower as we are increase in the offset, and then it becomes very small here. Okay, so we have high peak, and then we have low here. Okay, so the amplitude is decrease. Okay, so we will use now, in order to find this, will use now a relation that is called intercept and the gradient. Okay, we'll use the intercept and the gradient. The intercept is the first trace. The gradient is measuring the differences between the amplitude from the near to the far. Okay, so this is the relation, because we need to notice the change of the amplitude with offset. As the amplitude is changing with offset, okay, what about this change? What is this change? So we need to know this change in order to classify our reservoir. So now you will have here this relation between the reflection amplitude and then the incident angle. Okay, so we need to find the angle and then the amount of the angle and then the amount of amplitude. The amplitude will be divided as positive and negative. Positive as you have peak, and negative you have trough. Okay, and then this is the 0 point here between positive and negative, and then you have the incident angle. Try to find here, like this one. We have the near here, maybe like the angle, maybe 5 or 6 or maybe 10 degree. Okay, then you are going to find the 10 degree here. This will be like this degrees, then 0, and then maybe this is the 10. Okay, this 10, and then you will find the amplitude here. You will measure the amplitude here. So if you find the amplitude, of course, this will be peak. So of course it will be at this area because this is positive. Okay, so we are going to put the amplitude, the point here. Okay, like this one. So we are going to, if this is like 10 degree and then the amplitude positive, of course, so maybe like here, okay? And then we are going to the second one. Of course, the second trace will have different angle. Maybe this is 10, maybe this is 12. So the 12 degree will be found here. And then we will measure the amplitude here. We'll find the amplitude, the amount of the amplitude, of course, it will be positive because this is peak, all of this is peak. So you are going to find the point, which is maybe here, and you will repeat all of this till we found that the far offset here, still we have peak. So this is will not change, and this is not changed to trough. So you have here also peak. So you'll find that it's you have a peak also, still you are in positive. So try to connect all of this. You will find this one. Okay. So this is class one. And this is what we expressed using class one. Start with the intercept, which is the intercept here is positive, A is positive, and the gradient, if you are using this gradient, you will find this gradient is negative, okay? Because this gradient is decreased. So the gradient we are expressing using B. So the B, sorry, the B here is negative. Okay, so the negative here B, so you have A positive, B negative. So this is class one. Okay. Then for class 2B, class 2B here, you will find that we will start also with peak. So the A will be positive, and then you will find the amplitude is decreased till it reverse it to be trough. And this trough becomes a small negative and the big negative here. Okay. So this is like this one. It's starting from intercept, which is positive, and then the amplitude is decreased till reaches zero here at that area. The corresponding is here, okay? And then after this zero, it continue to have here small trough and then big trough here. So small trough, which is negative, and then continue. So this is class 2B. And then going to class 2, like this one, you will start with, this is our reservoir, top reservoir. So we'll start with trough. So the intercept, which is A, will be negative, and then you will have your uh, amplitude changing from low here, then it becomes greater in negative, greater in negative. So the B here will be negative. So this will be the trend. Okay. And then also for class 3, you have your reservoir here. So you are starting with high amplitude, which is high trough. And then this trough starting with negative. So we'll start with negative. Okay. The intercept. And then the gradient will be increase. I mean, you have here negative, maybe negative 0.3, but here you will have negative 0.7. Okay, so it's what we can express here like class 3. And then for class 4, you are starting here with high amplitude, which is trough, negative, like maybe 0.8, and then it decreased as you are increasing the offset. So you will find that maybe ending with 0.3. So like this one. So from negative 0.8 to negative 0.3. So the B may be, the gradient here will be increase. So it will be like this one. Okay. So this is the classes of the reservoir. You are just doing the cross plot between the angle and the intercept and the angle of incident. Okay, so you are going to have, what is your reservoir? You will find your reservoir one of these classes, maybe this class, maybe this one, maybe this one, maybe this one, maybe this one. So you have four different classes, 1, 2, 3, 4, and of course 2B. So try to find which reservoir. If you have an area and you have the drilled wells here, so you have the shear log and you have the B wave log, sonic compressional and sonic shear. So you can do the AVO modeling um, for your reservoir, and then you are looking to your reservoir. Is it class 1, class 2, class 3, class 4, 2B? If you found that your reservoir for this well is class 2B, and then you try another well and you find also this gas sand is class 2B, so you have your gas reservoir in your seismic cube expressed by class 2B. So you can generate a cube of intercept and the gradient, or you can use the intercept and the gradient cube if the processing delivered this one to you, or you can generate use your by yourself, and then you can try to track to tell the software, I have the class 2B, so I need to track the class 2B all around the seismic data at the reservoir level. So you may be able to find the distribution of the gas sand in the 3D. Okay, even you didn't drill some areas, so you will find that maybe you have the same response. So this is maybe you have like a qualitative analysis. You have here maybe expected you have a gas sand. Okay, so of course you need to do seismic inversion after that in order to make sure that, of course, this is you moved from qualitative to quantitative.